When we picture medieval warfare, our minds immediately populate the battlefield with cinematic imagery. We envision a world of chaotic savagery, where combat is governed by raw emotion and brute force. But the historical chronicles and pop culture depictions we rely on heavily contradict the actual, immutable laws of physics. Consider the famous accounts of medieval biological warfare, where besieging armies supposedly catapulted plague-ridden corpses over city walls to eradicate the defenders. Or the narrative of the crossbow, a weapon so devastating to the armored nobility that the Pope supposedly banned it entirely from Christian battlefields. And then there is the persistent belief that a single arrow could effortlessly punch through the iron links of a knight's chainmail. To dismantle these historical exaggerations, we have to examine the exact mechanical limits of early siege engines, then calculate the kinetic energy of a crossbow bolt, and analyze the actual material science of medieval armor. By stripping away centuries of dramatic storytelling and applying modern engineering analysis, the reality of medieval combat emerges. It was a practice dictated by strict mathematical constraints, rather than simple barbarism. The 1346 Siege of Kaffa is widely cited as the origin point for the Black Death in Europe. According to the legend, the Mongol army weaponized the plague by loading infected cadavers into their artillery and hurling them into the Genoese trading post. The entire foundation of this biological warfare claim rests on a single narrative written in 1348 by a Genoese notary named Gabriele de Mussi. Historical records later proved de Mussi never left his hometown in Italy. He was entirely absent from the siege he described. To understand why his account fails physically, we must look at the dominant siege engine of the mid-14th century, the mangonel. The mangonel is a traction trebuchet operated by teams of humans pulling ropes to swing the throwing arm, relying entirely on human muscle rather than gravity-fed counterweights. A side-by-side physics comparison shows a standard stone projectile versus a human body. A mangonel operated by 10 men generates a combined pull weight of 600 kilograms. To clear a 10-meter wall, a 70-kilogram payload requires a release velocity of 20 meters per second. But a human body is not aerodynamic. The extreme drag and asymmetrical mass of a flailing corpse cause rapid deceleration, instantly destroying the weapon's trajectory arc. Attempting to launch a dead body with a rope pull engine is equivalent to firing an open parachute from a slingshot. The kinetic energy is swallowed by air resistance. Contemporaneous proof exists of this failure. During the 1099 siege of Jerusalem, Crusaders attempted to launch a living spy over the walls using a mangonel. His weight was too much for the traction trebuchet, causing him to fall well short of the ramparts and break his neck. By 1340, larger counterweight trebuchets did exist and possessed the kinetic energy to hurl heavy loads like dead horses. However, accounts of animal corpses being weaponized at sieges like Thun-Levec and Karlstein were written centuries after the fact by non-eyewitnesses. These authors ignored the impossible approach angles required to lob such payloads into steep fortresses. The actual vector for disease in a medieval siege was highly localized. Months of starvation and extreme close quarters facilitated the transmission of zoonotic pathogens, usually through contaminated ground wells and zero sanitation. The concept of medieval biological warfare is a post facto myth. It ignores the strict energy transfer limits of rope pull artillery and overwrites the grim, naturally occurring realities of siege hygiene with cinematic fiction. While siege engines struggled with payload aerodynamics, personal infantry weapons achieved lethal efficiency. The most decisive of these was the crossbow. The human pursuit of lethal distance weaponry dates back well into antiquity. Thucydides documented early chemical warfare during the Peloponnesian War, where Spartan allies blasted sulfur and pitch at the fort of Delium in 423 BC. The crossbow itself originated in 4th century BC China. Its armor-piercing capabilities were so effective that it rendered traditional chariot warfare entirely obsolete, forcing a total reorganization of military tactics along the Chinese frontiers. When the weapon resurfaced as a handheld device in medieval Europe around the 10th century, it brought a terrifying mechanical advantage to the battlefield. That advantage relied on devices like the windlass or the crankakin. A crankakin is a mechanical ratcheting device used to draw back the heavy bowstring. By turning a crank, the archer uses gears to pull a draw weight far exceeding human physical limits, storing massive potential energy mechanically. This stored energy meant a peasant with basic practice could unleash a bolt with enough kinetic force to pierce the armor of an elite knight. This knight had trained exclusively for combat since childhood. In the context of the Middle Ages, the crossbow functioned like modern asymmetrical warfare. It bypassed the traditional feudal hierarchy, allowing a cheap, mass-produced infantry weapon to neutralize the most expensive military asset on the field, the armored horseman. This lethal democratization of force caused massive legal and moral backlash among the ruling class. The outrage culminated in 1139, when Pope Innocent II convened the Second Lateran Council to establish international arms control. The resulting decree, Canon 29, explicitly attacked the weapon, stating, "We prohibit under anathema that murderous art of crossbowmen and archers, which is hateful to God, to be employed against Christians from now on." This attempt at arms control failed almost immediately. Conrad III of the Holy Roman Empire observed the ban within his domains for exactly 13 years, before the military reality of his neighbors forced him to rearm his soldiers with crossbows to remain competitive. The hypocrisy of the ban was cemented by the era's commanders. Richard the Lionheart, the most famous Christian crusader of the 12th century, actively deployed mounted crossbowmen and was an expert marksman himself. While the velocity of the missile was grim enough, the terror of the weapon was largely psychological. Actual European poisoned weapons, like arrows laced with toxic monkshood, were exceedingly rare, yet the fear of a sudden, invisible death from a distance remained. The Church's ban evaporated because, in the brutal calculus of war, the tactical utility and raw kinetic advantage of a weapon will always override moral decrees and established social orders. This brings us to the final major myth, the pervasive belief that the kinetic energy of the crossbow and the English longbow instantly rendered chainmail obsolete. To understand why armor survived, we have to define its specific construction. Cheap, butted mail features rings simply bent together, which burst open under stress. Historically accurate military armor is riveted mail, where every individual overlapping iron ring is punched and sealed tightly with a steel pin. Furthermore, mail was never worn directly over the body. It required a gambeson to function properly. A gambeson is a highly compressed, thickly quilted defensive jacket, usually made of dense linen or wool, worn underneath the iron rings. This cross-section data visualization models the results of peer-reviewed stress tests conducted by the Royal Armouries in Leeds. It shows exactly how this layered material science reacts to incoming projectiles when outfitted on a yielding human target. Rather than piercing straight through, the kinetic energy of the arrow is caught by the interwoven rings. Because the rings are riveted, they don't split. Instead, they distribute the point force widely across the surface area, while the thick gambeson safely absorbs the resulting blunt force trauma. This energy dissipation was highly effective, even against the famous bodkin point. A bodkin is an arrowhead characterized by a narrow, square-shaped iron spike designed specifically to defeat armor. But because bodkins were forged from relatively soft iron, they often deformed, blunted, or snapped upon impact with high-quality steel rings. The historical reality is that due to this highly efficient energy dissipation, riveted mail remained the primary infantry defense across Europe well into the 1400s, which poses a logical question. If riveted chainmail was so mechanically resilient, why did armies eventually transition to full plate armor? This schematic animation illustrates the true catalyst. It was an industrial advancement, the application of the water-powered trip hammer. A trip hammer is a massive mechanical forge raised by a rotating water wheel and dropped by gravity. This infrastructure made it economically viable to mass-produce large, uniform steel plates for the first time. Armor did not fail overnight due to arrows. It evolved in lockstep with the industrial capacity to forge stronger steel, proving that the evolution of military hardware is driven strictly by economic infrastructure and manufacturing capability. When we analyze the mechanics of the past, the romanticized myths of antiquity quickly dissolve. The cinematic fantasy of flying, plague-ridden corpses gives way to the stark reality of contaminated ground wells and the strict payload weight limits of the traction trebuchet. The moral outrage of the papal crossbow ban was completely neutralized by the unstoppable mechanical efficiency of the crankwin gear. And the popular assumption that arrows rendered chainmail completely useless is corrected by the resilient metallurgy of riveted iron rings and the eventual dominance of the water-powered trip hammer. History is not a fantasy novel written by remote chroniclers. It is an unbroken timeline governed by strict, measurable physical laws. When we discard the exaggerated accounts of non-eyewitnesses and apply the rigors of physics and engineering, the true ingenuity and the brutal reality of our ancestors comes into sharp, undeniable focus.